Fusing UDP-based any queries. Oh, no, right here. Right up here is great.
Good morning. This is about DNS and not DNSSEC, which is weird for me. We can go to the next slide.
You've actually got the...
Oh, I got the slide thing?
That little green arrow right there?
Green arrow. Because the problem that we've been having that I'm trying to address here is that about a year ago, people started attacking DNS servers with any queries. And there was a talk or a panel session at the previous NANOG meeting in Dallas that talked about this. It's widespread. Every operator has been seeing this. Since then, we've seen those kind of abate a bit, but we've seen a proliferation of more any-based queries. And this is any queries coming over UDP, not TCP, to be a little more specific about this. We see the attack on our servers not necessarily as us as the victim, but us as the unwitting participant in passing traffic downward to the victim, which is a bad thing. The impact of the attacks are that we have to mitigate DDoS. It's a DDoS attack. It's higher cost for everybody involved. The mitigations, briefly, that we can go to this is adding capacity to make bigger servers. If we were the intended victim, we have to add more bandwidth and more servers and all that. But since we're just reflecting these attacks down to the real victim, we're actually adding more fuel to the fire for this. So adding more capacity really isn't the real answer we want to get into. Response rate limiting is now a much talked about response to this, mitigation to this, that was brought up in the network security session yesterday. And I want to, this is not the solution we're looking at, but I think it's a very compelling solution. And it's a response rate limiting. That's very significant. People have been calling this some people call it a resource rate limiting. The response is the important part of how this works, and it's important to keep that in mind. And the wording I have here, scales only so much, is actually strong. I actually wanted to change that wording. It's not that this has a scaling limit. It's that this still puts burden on the runtime environment to defend against this. And I'd like to take that out. I'd like to take it out of the runtime environment in the defense. The third mitigation I listed here is to use a DNS feature called refused. In the DNS protocol, you're allowed to refuse to answer any question you want. It's your prerogative. We have kind of observed that the any queries themselves have a limited positive use, but a huge negative use these days is growing, and we'd like to just say, okay, we're not going to answer anyone asking us for any information, any query over UDP. TCP is fine. It's fine giving away the information, but because of the nature of attacks, if we could just cut out the UDP part, we'd like to say that's what we're going to do. The storyline is that in late December we did this. We turned off answering any queries over UDP, and we listened to the complaints that rolled in. Whenever you make a change, you get complaints. We got a couple of reasons why it was a bad thing for some people, and a lot of people told us how we should be doing things instead of the way that we were doing things. In response to that, we're still refusing to this day. We are looking at response rate limiting as an interim solution. We call it interim because we like to go back to where we are today eventually and just say, let's not do this. But we realize that we're going to have a larger discussion before we get there. What we discovered in the time that we've turned off these queries and just refusing them, we found out that there were two basic earnest reasons for using these queries over UDP. Many people know about the second one. Their mail forwarders ask for this. It's been a well-known problem. We see that, and there are other ways to get the information. The first one, the domain name registries, some of them actually do pre-delegation checks. If you go to some TLDs and say, I want a name, they'll go off and say, are your name servers running correctly? And this is not every registry out there does the same thing. In fact, one customer of ours said they had 4 problems. I contacted the first 2, and they said, we no longer require that check over any over UDP. The third one really wanted it, so we want to talk about that. Also, the suggested fixes we got, they were varied, which kind of gave evidence that there really isn't a quick fix to this anywhere in the protocol. And I think everyone agrees to that. So why did I bother to do a lightning talk on this? We want to start a conversation. This is not a final report that we're doing this, but we want to go out there and raise awareness that this kind of query that we're seeing has fallen to become a tool of the evil, not a tool of the good anymore. And we don't really need to have it. As a protocol engineer, you say that this is a good part of the protocol. It's very nice and elegant. It fits in the model of everything. But as an operator, where you're looking at different goals and objectives in running the network, this is something which has just become abused. It's like putting a faster car on the street for someone to steal. So we really have shifted this from a good thing to it's a burden to us. So we'd like to say, can we just not? Can nobody use it? Because we find out that there really are only corner cases using this, and there are alternatives out there. So that's what we're trying to promote here. Now, there are a lot of critiques on this approach. We're picking on UDP-based any, even knowing that there are other alternatives for the bad guys to come and do the same thing. But they're using this. This is what we're seeing right now, and it's one thing that we say, okay, we can knock this off. When it comes to some of the other alternatives, we can do the same thing there. There are a lot of things available that can amplify the response. And in many cases, most of those queries are queries that no normal person would ever actually issue to a DNS server. And we can go at that one after one. So we're coming to the operator community and talking about this way. And I think, and of course, the reason why it's the start of a conversation, I know there's a lot of discussion to be had about whether this is a good idea or not. And that's why I want to come up now, and I'll leave some time for questions at this. So I'm going to stop talking now. And someone said they were going to bug me at some point, but he's still sitting down. So, nope, he's moving. He's walking. He guaranteed me he'd bug me about something. John Christoph. Let me try to.
How about now? There we go. I wasn't actually going to come up, Ed, but since you've forced my hand, so I think it's obviously obvious to you, but maybe not the other people, this is a very short-lived solution for a more general problem. But something else perhaps I've been wondering about for a while is that if it wasn't for DNS and perhaps NTP, I wonder, would we be allowing any UDP across the internet these days? Because it seems to be, maybe those two protocols seem to be the only thing that's kind of keeping significant number of networks from filtering UDP completely off of existence. In part because of this problem, but possibly the others as well. But for spoofing and uncontrolled flows and that sort of thing.
Yeah, I agree with that. I think the first D and D DOS is because we allow this fire and forget across the ISPs, and it would be nice to stop that if we could figure out a way to do that.
Hi, Dave Temkin, Netflix. I don't think we're really in a position where we could block UDP on the internet, but there's certainly plenty of legitimate uses. But this is not necessarily a unique problem. If you look at, I think it was BitTag issued like a best practices document regarding specifically SNMP to residential networks due to a similar problem, because people were using the fact that numerous CPEs are configured to allow, with public as the community, and you could just send one packet and cause a flood back. Is this something more so where it needs to be more targeted like that, instead of just suggesting that, we need to block it altogether?
It's hard to, we've tried different things like whitelisting and letting some people issue these queries. The DNS just doesn't lend itself to that kind of localization. It's a little harder to constrain this. But there are like I said at one time, I would like to just stop port 53 from transiting networks, have it come straight to us. Right. There are ways to go this. It's a lot of work in there. And like I said, we have to figure out what's the best way to do it, because I think protocol engineering, I used to be there a lot, and it was, here's what we go after. But in operations, we have a whole different set of what we're after. Right. And that's what's happening here, is we're trying to realize that really good, fast cars aren't the best thing on a congested street.
Thanks.
All right, thank you very much. Okay, next up we have Hamid Lalani from Telescent.
Okay, my name is Hamid Lalani, and I am from a small company which is a Caltech incubated company, which is just in the process of spinning out from Caltech. And we are and I wanted to bring this up to discuss the idea of layer 0 automation and what it means. And I'm sure all of you can look at that picture. That picture on the left is actually your competitor's data site. The picture in the middle is your data site. And we hope that in the future, everybody's data site will look like the ones on the right. The problem opportunity that we think is that every layer of the OSI stack is pretty much software defined today, except for layer 0. And I checked, I don't think, when I checked on Wikipedia, and there is really no clear definition of layer 0 anywhere. But most people understand layer 1 to layer 7. And the layer 0 is below, obviously, layer 1, which is the fiber optic cable. And the manifestation of that in the data center is the fiber optic patch panel. And today, that is part of that network that is still manually configured. Needless to say, you guys probably know more about the shortcomings of that part of the network than I can ever explain, because I've not been a data center operator myself. So this is kind of secondhand knowledge as far as I'm concerned. But most research and most study say that 50 to 80% of network outages are usually caused by some form of human error. And so what this has transpired into the last 20 years of managing large networks is people have become very conservative, and they have this unspoken, unwritten best practice of it ain't broke, don't touch it. And that's how most networks are operated. And in the process, what happens is that people over-provision networks just because they don't want to touch it. And we think there is probably an opportunity to actually automate that layer and bring it back into the toolkit of the network operator, so the network operator can actually manage even that layer just like he manages, or he or she manages, all the other layer network stacks. And since the three words have to be spoken anytime these days, which is SDN, which is about bringing the network to essentially respond to the layer 7 and above. So how do you make the layer more? How do you make the network more dynamic? We like to propose that maybe even layer 0 can be looked upon as one more tool in the toolkit of SDN, so that you can actually optimize the nature of the network, the resources of the network without without taking the risk of actually essentially causing some sort of an error, which could be much more costly than the benefits it might fail. So one of the things that we're trying to do is to kind of bring in the community over here to see if there is a way to raise the level of confidence in the way layer 0 is managed, and therefore can you actually optimize it rather than over-provisioning it as we have been doing in the past few years. So obviously this is not a problem that has not been known for a while, and a lot of effort, a lot of activity has transpired in the last few years, and some of the founders of this company at Caltech actually tried to solve it with very sophisticated technology like MEMS and photonic switching and things like that. Unfortunately, as you can tell, the cost of those things have to compete with the manual patch panel, or at least be in the ballpark. Uses of layer 1 switching to actually accomplish the same thing can be very, very expensive. So cost is one issue. The second one big issue is scalability. It's kind of easy to make a 200-port switch, or maybe even an 800-port switch. But when you go into a meet-me room and you have 60,000 ports, it's hard to see when will be the MEMS switch available at 60,000 ports, and at what cost, and at what size. So this team, so we've come up with kind of a relatively elegant very simple hardware but very sophisticated software solution to solve this problem. And so it is actually a switch which is just like your manual patch panel. So essentially, the one in the middle, the red thing that you see in that diagram, it just sits right next to your top of the rack switch and all the servers below it. And this particular configuration has 1,008 duplex ports. And you can go to the website and all that, and you can study about the product. But the idea is it uses off-the-shelf parts. Everything that we build comes from made in China today. So we use the same equipment that T Connectivity or 3M or Huawei or somebody like that will buy from the same suppliers and pull together this manual patch panel. The difference we have is we have a off-the-shelf pick and place robotic arm along with the switch, along with the thing, which is on the picture on the right, lower picture on the right, there is a little arm which has a robotic arm. And that robotic arm actually does the configuration based on what you provide to the computer that you want to change port 7 to port 32. And it does this. The invention here is, so these people have tried these things in the past. The difference here is that the algorithm that drives the robot is the breakthrough that the folks at Caltech came up with, which is based on the theory of knots and braids. Now, I'm sure some people are already Googling what is knots and braids, and you can see it's a 700-year-old mathematical theory, which is usually used in string theory. And the closest application of this thing is in genetic engineering, where they actually essentially define the helixes and the DNA helixes of how they would operate. So that's the thing. What I wanted to start the conversation here was to actually see how something like this, which is very cost-effective and can scale just like a manual patch panel, can be used in the data center. And I just wanted to make sure I go through a couple of apps and then open it up for questions so that people can look at it. Well, one of the big apps that we've been working with some beta sites in the US today are what they call smart hands. In this case, as you can see, the automated patch panel could actually be shared between the co-location cages around it. And today, you could actually make a change. So let's assume that XYZ company has a colo location in 1 Wilshire Boulevard at the Courtside data center. The XYZ company might be in Mountain View, and they want to make a change in their co-location physical infrastructure. Today, they actually hire smart hands, and the smart hands takes about 24 to 48 hours and has the risk of making a mistake and all that, and they make the change. But in this case, they could actually just tunnel into a GUI and make the change online. And the changes would happen in minutes, maybe about 120 seconds at the most, from one port to the other. And because the computer does it, the record keeping is computerized, the inventory is computerized, so even if the change has to be relooked, 3 months from now, everything will be there. You don't have to worry about records and all that. Because and those are the kind of things that, so that's kind of one application. The other application is where you could actually have something like an open flow interface down to the switch, and the switch can decide, and switch can respond to requirements of whether you're going from one type of application where you're using certain resources in the physical architecture, and you want to switch to the other architecture. There are applications such as these. So we have kind of listed a few applications. You can download the app, or download the presentation, and we would love to get some feedback from the user community. And finally, I'd like to leave you with something to smile about. So you could do that, and that's my email, and I'd love to hear from any of you during the meeting or after the meeting. And there is a demo actually on our website, so if you send me an email, I can send you a link, and you can actually see the Caltech demo. of how this product works. Thank you.
Great, thank you very much. I think we have time for a question or two if anybody has any.
Brian Dixon, VeriSign. Couple of quick questions. One is, does the device label the cables physically?
Each of the cables and the port are numbered. So the numbering actually is the way we label it. But there are other ways you could do it, but at the moment it does not, okay. If you what you're thinking about. But actually, one thing it does, every time it actually makes a configuration, it does clean the label. Clean the fiber. And so the fiber cleaning is actually taken away from the human interface.
And is it able to replace a defective cable? Is that one of the functions that it can do?
I'm sorry, which cable?
Is it able to replace a dysfunctioning cable?
Yes.
Okay.
Yeah, you could have spare cables in the system, and you can actually replace it if that's the way. Now, one of the biggest applications, which I didn't get a chance to show you, was one of the big things that happens a lot is transceiver failure. And this could actually solve the transceiver failure without a truck roll or without sending anybody out there, if you didn't have a redundant hot standby, which are not cheap.
Okay, thank you very much. Okay, and now we have Scott Whyte from Google, our last lightning talk.
Thanks. All right, so thanks to Josh Snowhorn and his roller coasters and his buckets of rum, I have 10 minutes to talk, and my brain is not functioning. So I'm going to speak very slowly, and hopefully will remain coherent the whole time. So Project Cardigan, an SDN-controlled exchange fabric. So networking is many things to many people in this room, but essentially I claim now networking is boring. Why is networking boring? Well, it's in a bit of a rut in a lot of different ways, for a lot of good reasons maybe, but I mean, we started with 10 meg Ethernet and then 100 meg Ethernet and then 1 gig Ethernet and then 10 gig Ethernet. Now we're at 100 gig Ethernet. And, with RAM, we've managed to, when I started, we had even less than 50,000 routes, but we thought everything would break at 100,000 routes. Now we're cramming almost 500,000 routes into RAM, and we'll double that shortly soon, I'm sure. So, what if we stopped and thought about what if we tried to do some things differently? What might it look like? Might not change anything, might change something in some small way. And of course, that leads us to the sexy software-defined networking. Software-defined networking is another one of those things that, is all singing, all dancing at this point, means everything to everyone. But some people got together in New Zealand, basically, and thought, well, what if we thought of software-defined networking as being, an enabler for networking, very similar to what open source was to operating systems, right? If it allows the user of the device to actually reach down and have more control over it. And what, in that context, that earlier question of what might you do differently with networking becomes slightly more concrete. So the folks who I'm speaking of are mostly in New Zealand. There's an ISP down there, CityLink, who raised a point that they felt like internet exchanges would be a good potential starting point for some exploration here. And then there are a group of people down there in the research community and in the operational community who are interested in SDN, and they needed something to focus on. So basically, well, like I said, my brain's not functioning. So I don't really need to go over what an internet exchange is in here too much, but I think it is interesting to point out what an internet exchange is not. It's not a router, it's not a switch, it's not any particular type of enabling technology. In the end, An internet exchange is where you advertise things you want sent to you and where you push packets that you want to get vacuumed up. So that's a pretty generic description of what an IX is. So we came up with this Project Cardigan, which is an unfortunate name with some subtle New Zealand humor, which I won't try to explain here. Something to do with their sheep and wool, and I don't know. But basically, so phase one for this Project Cardigan was to get an SDN device onto the IX in Wellington. And so this was completed back in December. Basically, we took the picture there is a picture of this PK83290, which is a switch that actually supports OVS on the top. And that was convenient because these fellows in Brazil, CPQD, have this project they've been working on for a while called Route Flow. And what Route Flow does is it takes, essentially, it takes OpenFlow on the bottom and Quagga on the top, and it glues it together with some virtual machines. And it speaks OVS on the bottom. So we were able to take out OVS and put in this hardware that actually speaks OVS up the top, and it all just worked. And so essentially what we've got now is we've got a device on the IX that will accept the BGP packet through the switch, make its way through the VMs up to the Quagga instance. The Quagga instance will process the BGP update, change the Linux routing table in the VM, and then there's another process that will watchdog the changes and push them back down into the hardware. So voila, we've got an SDN control plane that's controlling local hardware. And this is the operational forum, so there we are. We have a route. Woohoo! But in the end, that's not really exciting, right? We have a route, and it's still pretty boring. So the next phase was fairly obvious, probably, to make it a full route server. So in the same time as we got it up, we basically then just added a bunch of routes so that everybody on the Wellington Internet Exchange could peer across it. So again, still pretty boring. Progress, but still pretty boring. A couple weeks after that, after a bit of hacking, to actually extend some of the functionality that existed in the route flow, something interesting happened. We actually brought up a second switch that was in a remote location in a different part of the city that was actually being controlled by the same OpenFlow controller. So now we've got an actual distributed router running in an internet exchange as a route server. And it's actually passing production customer traffic. In this case, it's REANS, which is a research network in New Zealand, but they were good enough to actually hook their office up to it and are running real traffic across it. So like it says there, big thanks to REANS and Dylan Hall for taking that step. So, now that we've got this interesting capability, what's the next step? Well, there's a couple different things we need to do. I mean, I showed one route. Okay, that's not too interesting. We've got the control plane proof of concept now. We need to start working on the data plane. We need to stress test the data plane and show that we can actually get routes in and out of the data plane. Sorry, I should say prefixes or fib entries in and out of the data plane in a reasonable time frame and scale. There's also some other things we can do with layer 2, to experimental things, I think. Probably the most directly interesting thing I think we're going to work on next is actually getting the fabric to enforce policy. So, I mean, we have this SDN, we have this capability of programming the fabric to only have reachability we want, to do exactly what we need. Well, let's run with that. Let's actually make the fabric enforce the security and prevent customers, participants from being able to hurt each other, and see how that simplifies operations and increases reliability. So that's really, I think, the next big step for us. So, in the end, hopefully, network is almost not quite so boring as it was. And here's a list of the folks in New Zealand who've been hard at work on this. So thanks to all of them. So, any questions about any of this? Cool.
Okay, thank you very much. Just one housekeeping item. This is your last chance to visit the NOG Lab if you haven't already. That's happening from 10:30 up until noon in Atlantis A. And right now we have a break sponsored by Netflix, and we will see you back in here at 11:30. Thank you.